Good afternoon, everyone. Thanks for coming for today's CWS seminar. So today we have Professor Stéphane Bordas from Luxembourg University, the Lake Tau team. So he's done quite a lot of research on the data-driven modeling, machine learning, artificial intelligence. So it's a good opportunity for us to learn from him. Thank you.
Thank you very much, Albert, for the introduction. So I'll do my best to convey messages in a clear way. There is a lot of material I'd like to cover today. I try to also do my best to fit within the water group, which is not trivial because most of my research is in solid mechanics. So I hope I will do justice to what I'm talking about, in particular to the work of the students and postdocs that led to this work. This is the University of Luxembourg. You can see the administrative building on that side, and you can see the student building that looks like an asteroid come directly from space. So this is a very modern campus. If you want to know more about what we're doing, you have here two QR codes that will normally lead you to the website and to the YouTube channel where we upload all the seminars that we host, as well as some of the lectures that we give in various topics. So so the team has been quite varied with over 54 nationalities over the years, so that's quite a nice thing, and we've been working on different topics. I started my research career in 1999, and now we've been working on things like energy, health, materials, environment, but specifically on methods and tools. So my specialty is not the applications, so not energy, materials, health, or environment. These are, I would say, applications that came more or less on their own with the comings and goings of funding and of people, in particular Marie Curie Fellows. And today I'll be presenting the work of 3 Marie Curie Fellows, if I manage to get things in time. To give you an idea in which fields we published, this is approximately what we've done. So the fields where we did not publish will be easier to actually summarize: political science, philosophy, art, geography, and business and geology. So in these fields we've not done anything. But in the others that are tagged here, there are at least a few papers to speak for the work of the students and postdocs in the group. And then if you want to look at it more in detail, you see that essentially most of the work was done in engineering, plus computer science, plus math. So there is quite a lot of papers in math journals. But what we consider as math is not pure math in any way. It's not even applied math in the sense that we do not even prove the convergence of the numerical algorithms that we develop. But we use the results of applied mathematicians that will tell you whether a method is convergent at which rate using a priori estimates. So we work with mathematicians that do these proofs, and we come up with new methods, and usually the mathematicians that work with us are going to tackle the proofs of convergence to make sure that we are not just lucky and we came up with an algorithm that happens to work, but that this will work every time under certain conditions. So if you're interested in visiting Gran Canaria, or rather in learning about advances in applied mechanics, you can consider coming to our conference in January 2026. We've had this conference now for 2 years with Stéphane, and Stéphane is in Galway and MIT and Wisconsin. And he with me decided to create this meeting in the middle of winter to be able to, it's only by invitation, so we would like to know what you would like to present if you're interested. And we keep it very small so that it's basically friends coming together to discuss topics that they are interested in. And it's related to the journal I've been editing now for 22 years. Which is called Advances in Applied Mechanics, and I'm a bit ashamed of saying this because I'm not at all in the same category, previously edited by von Kalman, von Mises, and Hill. So when Elsevier asked me to do this, I felt very small, and I thought it was a mistake. But it's been going on for now 12 years, and it's working quite nicely. So my goal is to make a connection between experiments, theory, and computations within one mechanics-related journal. So it's only about reviews, effectively. And now I'm going to start the interesting part of the talk. Sorry for this introduction, but because I come from elsewhere, it's, I think, always nice to have an idea of what's going on. So, if a lot of what people are talking about today relies on what they call machine learning, AI, and so on, and maybe a lot of you came today because you thought you were going to maybe learn something about AI, machine learning, data-driven methods, and so on. And in doing so, well, you made quite a big hypothesis, because you assume that because in the title of the talk is written machine learning, then maybe the talk has to do with machine learning, which is a big assumption, because most often it doesn't. But then what you're going to do is you're going to sit in this talk and hopefully pay attention, and you're going to essentially gather evidence about many things about the talk, whether what I wrote in the abstract has to do with what I'm talking about, which for now it doesn't, whether I'm a good or a bad speaker, am I able to convey evidence in a clear way, and next time you're going to see a different talk from someone else, you're going to use the evidence that you acquired today to modify your hypotheses about the world, because you will know, now I went to one more talk when someone told me about machine learning in the title, but did not say anything about machine learning in the talk, so maybe I'm not going to go to this talk. Or maybe you'll think, I thought Stéphane Bordas was a good speaker, but now I heard his talk and I'm actually convinced he's absolutely abysmally bad, so I'm not going to go to a second talk. So essentially what you're doing is you're updating your vision of the world through evidence. And this is the way that we learn. This is, in fact, shown by psychologists. For example, Stanislas Dehaene at Collège de France. You can read his book, How We Learn, which explains the theory of learning. And according to him and many others, we learn in a Bayesian way, a bit like when we are a kid on a high chair. We drop something from the high chair, we drop it from the left hand and the right hand, and we put it on our head and see if it keeps dropping. So we're testing the laws of physics by experimenting with physics and the world around us, which is a way to do essentially Bayesian inference. But to do Bayesian inference, you need a prior, which means hypothesis about the world, and you need some evidence, which is what you see. And then what you do, which is very counterintuitive, is you compute internally the probability of what you're seeing being true. So I repeat, you compute the probability of what you're seeing being true. That makes no sense, because what you're seeing is there. So how can it be not true? But in fact, it's not true, or true not in vacuum, but with respect to your view of the world, which is the hypothesis. So you're essentially updating that every time, and your hypothesis is being updated as your new observation becomes incorporated into your view of the world, which is your prior. So your posterior knowledge is what you see, becomes your new prior. And then you will make another observation until you converge to your current view. And this is the way we learn, and this is the way machines learn, and this is probably the way that we can make progress in this so-called data-driven modeling and simulation. So I'm not inventing anything, I'm just explaining it in one way. This is absolutely not new. There is nothing new with what I just said. So what we typically do is we have an input, which is whatever, a set of variables, and we have an output, which is typically what we observe, so we call one x and the other y, and we're looking for the link, the mapping between x and y. And we have a lot of ways to do that. So historically what we did is we, for example, did experiments on a piece of steel, if we're talking about structural mechanics. For example, to know how many times you can pull and release a piece of steel or maybe a paper clip. If you bend to and fro a paper clip, eventually it will break. So there is a guy, Paris, that came up with a law that tells you how many times you can do that, depending on the type of alloy that you have. And this was an experimental law. You make experiments and you try to see if you can write a law down that fits what you actually see in the experiments. But you do the experiments once, in some warehouse somewhere in under certain conditions of temperature, pressure, and so on. And then you hope that this will carry out to real life. Now, what is going on, and this is more on the right-hand side of the screen, is that you are able, through, for example, this is, well, anyway, it doesn't matter what it is, but you can gather a lot of data from many sources. People in computer science we met yesterday are using so-called social networks data, like Instagram, to gather data about how people connect, what is the connectivity of the network, and so on, and how information flows. You can do a lot of work with only data, but in that case, you have no idea at all about the physical laws or any mathematical equations that could govern, let's say, something you could gather from Instagram data, which would be the probability that someone entering pub X in city Y has to take a picture that contains a Coca-Cola bottle, for example, which is of huge relevance to Coca-Cola, because what they want to know is, let's say, how do I advertise my product? Where should I put the images of my bottles so that people are most likely going to see them at the right time, so that I can influence them? So there is no equation for now that is going to tell you, if I enter this pub, I'm going to get that probability of seeing X or Y. But the data from Instagram can tell you that. And in my opinion, and this is an opinion which is largely shared, so again, nothing new, is that we are usually somewhere in between the case where we have a lot of information about the physics of the problem. For example, Newton's law, you know how fluid flows in a pipe, Poiseuille flow, whatever flow, Darcy's law, anything. Or on the other side, which is the data-driven approach, where you have only data, but you have nothing about understanding of the system, simply because no one wrote equations about Instagram. Newton wasn't there. I guess otherwise he would have done that. But apparently, for now, we have nothing that does that. And so what we are interested in, as many other people, is in adaptive models. So models that are built on equations. So this is where I'm coming from. So I'm much less on that side, which would be more the computer science side, the data side. I'm much more on that side because I'm very comfortable with equations, conservation laws, and so on. This is where I come from. And how we can update that using the data that we capture, and how can we do that fast. And so we've worked on a large variety of applications, and I'm going to show you now a few. The first one has to do with, okay. I hope, no, apparently not. Okay, yes. Good. Okay. Okay, so what we are interested in here, this is application number 1, is wind energy harvesting in cities. So the idea is, and there are many examples where people have thought that putting wind turbines in cities was an important thing, because you could use the fact that the city itself is acting as conduits for flow, which could create positive effects that you can use. And that was done in many places, and sometimes it was done in a weird way, because people did not take into account the wind directions that are prevalent in that particular city at that particular time in order to design the turbine, so, which obviously is not the best way. And it could also have impact on the way you design facades, and on pollution transport and all sorts of stuff. So understanding fluid flow, meaning wind flow in cities, is important, I think. We can just assume that if we are not agreeable with, what I just told you as arguments, we can just make that assumption. It's important to be able to do that, and what happens in reality is that you know approximately what the flow regimes will be. So you know where the wind is coming from, what is the amplitude, and what is the direction of that wind. And you would like to predict what will be the turbulence downstream of the building, because you may want to put a wind turbine there, and if you put a wind turbine in the turbulent area, you know that the output will be less than if you put it in a laminar area, for example. So you don't want the wind turbines to be too close to each other, because they may influence each other. You don't want them to be too close to another building, maybe, so you want to take that into account. unfortunately, the number of angles that the wind can take is not really predictable. I mean, you know a bit, but you don't know everything. And secondly, you do not want to do all the calculations for all the possible angles in order to perform your design, because that would be prohibitively expensive. If you want to do a direct numerical simulation or even a large eddy simulation of flow around the building, one building you may be able to do it. You may come up with multi-scale approaches, or unit cell or whatever. You can play tricks, but in essence, it's difficult to do these simulations in very refined ways, especially because the higher resolution you go, the more details become important, like what is on the facade, what is the state of the surface, is it rough, is it smooth, and so on. So the idea is to perform low fidelity Reynolds average Navier-Stokes, or RANS, I will use that term from now on, but to teach RANS to be more correct than it would normally be using large eddy simulations. So this is a so-called multi-fidelity approach, which Hussein taught me 2 days ago. And we see here that the idea is, how can you use effectively less computational cost and get the same accuracy out? So the questions that we ask are the following. So what data do we need? How do we make sure that the data actually makes sense? If we want to use machine learning, what method should we use? And how do we estimate the uncertainty of the machine learning model? So the idea is the following, that we will use RANS plus LES plus wind tunnels for validation. So the idea is you take LES, which is large eddy simulations, and you try to essentially parameterize it such that it fits with the wind tunnel calculations. And you assume this is now the ground truth, and you're going to train the model on certain angles. For example, 7.5 degrees, 15 degrees of wind, so you compute for different wind angles, and you try to figure out what is happening, and then you use that as a training set. So for RANS, we used the solver simple foam, and for LES, piso foam. And there are details here about the calculations that Anina Sarkic did. She was a Marie Curie fellow in the group and is now in Belgrade, and we are continuing to work together on this. So here are the wind tunnel results and how we fit the LES. So I'm passing that because it's not super interesting, and I'm going to go directly to how the output looks like. So we are able to predict effectively, quite accurately, using RANS, what goes on in a way that was trained using LES data. And the initial training data was only at 0 degrees and 45 degrees. And however, we're able to predict, of course, outside of this range. However, this is the same case always in machine learning. And I think I show that later, is that first of all, you need to be adaptive in your training, so you cannot just decide a priori where to train, because you do not know which part of the parameter landscape is going to be steep and which part is going to be shallow. So it could be that some change in one of the parameters is going to, within a certain parameter range, have an enormous impact on the quantity of interest. It could be that at other areas in the parameter space, nothing happens at all, everything is flat. So you want to sample the space in a way which makes sense, because otherwise you will spend energy and compute time doing things that are not helpful in decreasing the error. Okay, so the results, I will just summarize very quickly. There are papers where you can figure out how we did that in detail, and if you're interested, I will put you in touch with Anina, who is clearly the best person to talk about this. But so we performed so-called hyperparameter optimization to figure out what we should do in terms of training. And then, which I think, okay, I will just move directly there, which I think is the really important point, is that we perform feature selections which allowed us to figure out which of these observables here, or features, were, or parameters, were most important. So, and that can be done using a number of uncertainty quantification approaches, which allows you to detect, using your simulations, which of these parameters will be useful and which ones will not be so useful. And that was something which we did, and there are lots of results to show that. And at the end of the day, again, something that we started working on when Hussein Rappel, who is here now for a long time, did his PhD in my group. We started to think about uncertainties at that time. He was the first who started doing this work here in Luxembourg, and it is exactly the same with machine learning. So we started outside of that field of machine learning because simply we didn't need it. But in machine learning, everything is exactly the same. So if you have a neural network or some sort of artificial intelligence, whatever, as long as you do interpolation, meaning you stay in the range of the training set, you will be mostly okay, because you can actually prove that you can approximate anything with a neural network, so it will work. As soon as you get outside of the training range, it will fail, and that is just quite normal. And so what we did in the past with PhD student Saurabh Deshpande, who's now leading an AI in a large Indian company, what he did is to come up with essentially Bayesian neural networks of different types that were able to give you an idea of the confidence that you have on the output. So he did that for hyperelastic problems, where you have very large deformations of soft materials, but that can be done in any area. And clearly this is a way to go, because instead of having deterministic results that tell you that the pressure is whatever Pascal, now you have the pressure is, let's say, 200 Pascals plus or minus 10%, and we have a confidence interval of 98% that we are within that band. And I mean, in my opinion, this is in engineering what we should be trying to do, because we are certain of nothing, effectively. And that could give us a way to quantify the uncertainty for a given quantity of interest. And a message that I would like to convey, because I realized that I went very fast over these results simply because there is too much to explain. And I just want to tell you an idea, not that you remember the details. So what I would do is, what my experience says is that we cannot, in general, minimize the error. So when we say that we want to minimize the error of a simulation, this is not a proper statement. We should explain clearly what we minimize the error on. And we did a lot of work in biomechanics where this is extremely vital to take that into account. We cannot just, in general, minimize the error. We need to know with respect to what quantity of interest we are minimizing the error. And this has been a lot of the work we've done with Franz Schully, who is a mathematician in Uruguay now. He was in France before. And he is a very strong proponent of that. And we have created a series of special issues in Advances in Applied Mechanics only on error estimates, and in particular on goal-oriented error estimates, which tell you what happens, how to optimize the mesh to decrease the error on a certain quantity. If you're interested in average pressure or average velocity across a section, or I don't know, drag or anything else that's related to your calculation, then the mesh that will minimize the error on that particular quantity is vastly different from the mesh that will minimize the error on something completely different. Let's say you want to minimize drag, the mesh that will do that, minimize the error on drag, the mesh that will do that is completely different from the mesh that will minimize the error on average pressure, let's say. Maybe not, because it's related. So, but we need to, I could find another example. So you need to be aware of this. And when you're talking about errors, there are always several types of errors. There is the model error, which, in my opinion, I spent 10, 15 years of my career working only on the discretization error, meaning if you give me the problem, can I solve it properly? So can I solve the problem right? But my view after working for so long on that problem is that this is not the best problem to work on. If you want to work on a problem, work more on, are you solving the right problem? And thus, are you solving the problem right? So is the model correct, as opposed to is the way that I'm solving the model correct? So basically, am I choosing Navier-Stokes, and should I instead choose to solve, I don't know, just Stokes flow, because it's easier and it's faster, so given my quantity of interest, it's enough. Should I use turbulence or no turbulence? What model of turbulence should I use? You know, and so on. That is a difficult question, as opposed to saying, am I using the right solver for that? Which I'm not saying is an easy question, but it's a question that many people know how to answer using a lot of technical, let's call them tricks for people that don't know, and art and trade for people that do know. But it's essentially, you know how to solve today, you know how to solve a given equation, you know the methods that work, you know if you want to use DG, discontinuous Galerkin, or finite difference, or finite elements, when you use finite volumes, when not, if conservation of volume or mass is important, not important, and so on. So all that is known, so I try now to focus on selecting the best model as opposed to selecting the best discretization, and hopefully I will get to the part of the talk when I talk about this. The second application is a bit different. It has to do with CFD as well, but it's called, well, we called it industrial CVD reactor, which is chemical vapor deposition. So chemical vapor deposition is a process where you deposit a very thin layer of, let's call that anything, material upon another material. So here we have on the right-hand side what are called inserts, and we did that with a company in Luxembourg. The work was done by Eleni Koronaki and 2 PhD students, Paris and Jeremy. And this is really chemical engineering work. So you have here these inserts. These inserts are tools, and you want to cover the tools with a thin, very hard layer that you can then protect the tool with against abrasion or fracture. And the way it's done is you have these discs, and you have flow that comes in and out, and the flow contains, let's say, chemicals, to make it simple, so species. And because of the flow rate, the pressure, the velocity, and the temperature, there will be deposition and chemical reactions on the surface, which will create the deposition of that surface coating. And the problem is that depending on the flow conditions, you will get a thicker or thinner coating, and what you want is you have an homogeneous coating. So depending where you are in this reactor, you will get thinner or thicker coatings, and you don't want that. You want to have something homogeneous. But the complexity is that all these shapes are very different, as you can see, and also they are positioned at different places in the reactor. So the question is, can we have a way to relate what is going on in the reactor, so what comes in and what comes out, in order to maximize the homogeneity of this coating? So the quantity of interest in that case is very clear. This is the thickness being homogeneous. So this is a very challenging problem, and the way the company has been doing it is to do that using rules of thumb and being used to how it works. So, engineers have developed understanding of the process for generations, and they have this know-how in-house, and they know how it works. If I do that, that happens. If I do this, this happens, because they know the process. And what we wanted to do is to see if we could rediscover that process without knowing what the process was, using machine learning. So could we learn all the years of experience that these people have acquired by using machine learning? It's not so easy. So the equations are here. They are very standard equations. So reaction, advection, diffusion, and so on. Very standard. There is nothing groundbreaking here. It's all conservation of mass. And that's pretty much it. And momentum. So you have Navier-Stokes, and you have you have conservation of species. And then the question is, what is going on in these reactors, and how can you compute that faster? So the way to compute faster for us is to use what we call surrogate modeling. So surrogate models means we replace the highly computationally intensive simulation by a simulation which is less costly, but hopefully has a similar degree of information content. So we try to keep the information, decrease the cost. You can do that using a lot of methods, proper orthogonal decomposition, which is mostly linear, manifold learning, which is then non-linear. You can use all sorts of projections. You can today use machine learning, all sorts of methods that came up because of the surge of computational power. And to do that, therefore, we're going to do supervised learning, because we're going to tell the computer, these are the input parameters that you see here, and these are the output that we see here. And then the question is, how do we modify these parameters on the left to, and you see there are lots of parameters, right? It's not so simple. How do we link that to the quantity that we are interested in? And that is not such an easy thing. And Jeremy, who came in the group towards the end of that series of projects, we had 3 projects in a row with that company, is that you have here some categories that are, some features, meaning parameters. So in machine learning jargons, these things are parameters, but that are effectively numerical. So, for example, what could we take as numerical? Number of inserts on disk. So this is numerical value, 5, let's say. Recipe version. Okay, that's already not it could be a value if you say it's that you have 10, so it's 1 to 10. But you could have things like above disk model, below disk model, and so on. These are categorical, let's say, features or parameters. So they are not 1, 2, 3, but they are text. So, for example, I do this in such a way. I put this on the top of that. I remove this and move it there. So it's a process that people use in the design of these reactors that you can write in terms of natural language. And so naturally, not naturally, it was a great idea. What Jeremy wanted to do, now it's natural after the fact, but originally it was not so trivial, is to embed these ideas of natural language that you put inside your design procedure, inside the machine learning algorithm. So that you can say, the engineer comes and says, okay, my way of working is to do this, I do that, I do this, he or she describes what they do, and then you put that as an input. And then you see how that translates as an output, which you can do either numerically or by doing experiments in the actual chemical reactor. So what you need to do that is to transform the text into something computationally amenable. Obviously, these large language models, or at least natural language processing, is a natural way to do that, because you can embed all that know-how of experimental design and how you do the protocol. You could carry that out to other fields like biology and so on. All that can be written down in natural language. You transfer that into some number, and that number you use as an input. It's not that trivial, because that, of course, mapping is not unique, and so you can do a lot of stuff that makes no sense. But we also showed that you can do things that make sense. And then what is the advantage of that is that at the end, because you end up with a matrix, which you can picture here, that matrix is effectively a list of rows and columns, and they are vectors. So you can measure then, because you can measure how close 2 vectors are. So let's say that I have a set of parameters on the left here. If I transform that into this sort of codification, I will end up with, let's say, 1 vector or series of vectors. I can measure how collinear they are or how orthogonal they are, and I can tell you if one way of manufacturing is close or far from another, which means that I can compare much more easily something which is otherwise uncomparable, because if someone tells me I put this disk first and then I remove it, I put the second disk, I remove it, I put the third, and so on, all this is sort of descriptive but not very quantifiable, so that this method would ultimately, not yet now, allow us to quantify, let's say, in a number way, how close 2 approaches of design are. Okay, so practically speaking, so Jeremy used, and Paris and Eleni used clustering methods so that you can find common characteristics of production and the impact of the process parameters. and then they look at the output, which is the thickness distribution. And then they did that using NLP and without and with NLP. And okay, I'm not going to look at the results in detail, but I can tell you that the advantage is huge, and the company is already taking that on board and using it. So I think we can be happy about that. After that, we use, in that case, unsupervised learning, which is, so supervised learning you probably know. I tell you this is a horse, and I show you a picture of a horse, and I should show you this is a cat, and a picture of a cat, and so on, and I tell you cat, horse, you know. And unsupervised is, I tell you, this is how you play chess, play all the games that you can against yourself, and learn how to best play chess. This is AlphaGo, and so on, and AlphaFold type of approach, although AlphaFold was then also supervised. Okay, so then we did that, and we tried to see if we can, after clustering, get a surrogate model, come back, go the experimental design, make a sensitivity analysis. Problem is with sensitivity analysis is that it's very costly. You cannot just, do that for all parameters. You have too many parameters there. You cannot vary all of them. So that's why the clustering is very important, because you first cluster the output depending on the input, and it gives you regions, and in these regions you can then vary the parameters. And that's much more effective than just doing brute force and going to vary all parameters at a time, which is in fact not possible, because it's far too complex. And then at the end we see what the most influential inputs are, and we're able to do that in that way. Okay, and that what we are working on now, what effectively is generally working on, is to optimize the reactor setup by inverse uncertainty quantification. So this is another kettle of fish, because you not only need, okay, so for forward uncertainty quantification, just so to fix the terminology, forward means you have a set of equations, you have parameters in that equation. Let's say you have one parameter to make it simple. You will vary this parameter from 0 to 1 and take 10 values of that parameter. You need to make 10 calculations. Now you have two parameters, you need to make 10 to the power 2 calculation, 10 parameters, 10 to the power 10 calculations. So it blows up very quickly. And on top of that, the methods of sampling are usually converging very slowly. For example, Monte Carlo is converging in the root of n of the number of trials, which means you need really a lot of trials before you actually get anything. So if you do now reverse or inverse uncertainty quantification, what that means is that contrary to the direct uncertainty quantification, where you sample a probability distribution for the parameter, you need to take certain values of that parameter, but they are random, but they are random according to a certain law. And so you sample that law. Now you do the reverse, you measure something in real life, you get a probability distribution of that measurement, let's say the thickness, and you want to go back and have an idea what is the probability distribution of each of the parameters of the, let's say, chemical reactor that led to this uncertain output. So you have the uncertain output, and you want to get back to the original uncertainty on each parameter. And that's much more complex, but also much more useful, because it allows you to optimize the reactor setup, because you know now what are the what can be improved in terms of the variability of parameters, for example. So this is super useful. I mean, if you make that fit that to the mechanics, solid mechanics approach, it would be you take a brain, for example, of someone, you measure the deformation, and you want to go back to the probability distribution of Young's modulus and Poisson's ratio and shear modulus and viscosity and so on. So this is a way to identify parameters in an uncertain way. And yeah, that's it. So that's basically what we have been working on. And what is really cool, I want absolutely to talk about this, because so I started probably 4 years ago to work with Professor Alexander Skupin at the LCSB, who is working on astrocytes and neurons. And 2 years ago, I started working with Professor Anne Grunewald, who's also my life partner. And we started to work at the interface between computational cell biology and experimental cell biology. So what you see here is a little cell, and maybe you will learn something today. so that cell is called an astrocyte. So as you can see, it looks like a star, hence the name astrocyte. So if you learn astrophysics or something, then you can always relate to this field. And that thing has what are called feet, which are here, and processes, which are these little branches here. And they connect to two other types of cells, the blood flow and the neurons. And for a long time they were neglected. People thought these little things are useless. They are just here as support, but mechanical support, so that the neurons are not floating around the brain, kind of a bit limited as a scaffolding, essentially. And but in the last 15 years, people figured out that this is not the case, and that these things are carrying nutriments from the bloodstream to the neuron, and taking garbage out from the neurons back to the bloodstream. So it's effectively some sort of bumper between the neurons and the bloodstream. So, okay, cool. Then the problem is that some people, of course, develop neurodegenerative diseases like Parkinson, and others don't. So part of that is genetic, part of that is environmental, and this is now known. And one of the hypotheses is that what can happen is that these astrocytes here become too greedy, and instead of giving the food, let's say, in terms of whatever molecule, doesn't matter, to the neurons, what they do is they keep it to themselves to keep their own metabolism going. But they do not give the food to the neuron, which start to deteriorate because they are underpowered, let's say, not enough glucose or lactate or whatever is channeled. So what we looked at is how we can figure out, with the thesis of Sofia Farina, who is now in Bern working on a similar project in Switzerland. So what can we say about the metabolism of these cells? And so metabolism may not look like a chemical reactor, but it's pretty much exactly the same thing. So you have a chemical reactor, which is the astrocyte. It has different sites in there, which are the mitochondria. They are the processing units of the cell, and they also make ATP, which is adenosine triphosphate, which is what you use to transfer energy in the body. And that stuff is being generated, or not, in a pretty efficient, or not. What we wanted to see is what is the influence of the shape of these astrocytes on their ability to process food from the bloodstream and make it available to neurons not to degenerate. And so we did that using very advanced computational techniques, and which allowed us to figure quite some very interesting things out about the position of the mitochondria inside the astrocyte, the calcium waves, because there is a lot of calcium going on in the neurological system. And so that was super interesting, and we are continuing that through several projects with Anna and Alex. And just want to tell you that we used exactly the same method that was used for XGBoost, with all that sort of clustering methods and so on, was used exactly as is. So out of the box, no change, from the chemical reactor to the astrocyte, and worked immediately. So this is one of the things where you thought, wow, this is unbelievable, because if I had dreamt it, it would not have worked. But it actually directly out of the box worked, and allowed us to look at the influence of the position of the mitochondria in the astrocyte on the ability of the astrocyte to generate optimally energy, food for the neuron. So this is a great, for me, example of multidisciplinarity that went right, because it's easier to show what went right, because it's much less frequent than what went wrong, and the presentation would be far too long if I focus on what didn't work. So, but this was really amazing. I was very, very happy with that. And I'd like just to show you one last thing. I know that I don't have the time, but I hope that you will indulge me a little bit, not because I think what I'm saying is, that I'm so important, but I think that the person in question, Pratik Sochte, in my team, has done outstanding work, so I would really like to at least talk about what he did. He was also a Marie Curie Fellow, and then he continued on different topics during his stay in Luxembourg, which is coming to an end, unfortunately. And he worked with Volkswagen, with the Fraunhofer Institute in particular, and he worked really on shallow water versus Navier-Stokes, and on adaptive model selection. So the idea being that you want to do things like this. So you want to fill some containers, you want to do some cleaning with jets, or you want to do things like melting of whatever you're interested in. In his case, he was interested, and still is, in the automotive industry because the Fraunhofer is interested in this. And so he did a lot of work using, you can imagine, SPH or equivalent of SPH, so smooth particle hydrodynamics, which if you're in water you probably heard of. This was, well, let's not go into history, but incepted by Monaghan in the field of astrophysics at the beginning, and was then used later. So this is a method which in its original form is not consistent, meaning that it's not able to reproduce even a constant field, which is a problem because you cannot show convergence. In fact, you can show divergence of the method if you use it in the original form. But a lot of mathematicians worked on that and improved it, linked it to reproducing kernel particle methods, RKPM, and there is a huge amount of literature in that field. If you're interested, you can write to me and I link you up to that. We also wrote a book on material point method, which is quite related. Okay, so that's a question. How do you start from a bulk fluid, like here, and how do you transform it into something that is more amenable to large-scale simulations? You don't want to use Navier-Stokes everywhere, because this is super expensive. You want to use it only where needed, and where it's not needed, you want to use shallow water equations, because you have far fewer unknowns, and it's much easier to handle. So the question is, how do you switch from one model to another model? And so again, and anybody interested in this, I will give you the contact to Pratik, because he is really very good at this. So problem is, you don't know the interface a priori. You cannot say where the flow is going to become thin and where it's going to stay bulky. You have no idea, so you need to figure it out. And the interface is also moving. It could be that some very thin surface is now let's say, conglomerating into another bulky area in the future. It's not only one way. So it's a difficult topic. Okay, that's it. So you want to adaptively choose the model and the governing equation. So you don't just want to choose the discretization, which is quite easy. It's adaptive discretization. Everybody does that now. But choosing the model is still an open problem. So if you want to solve, something really interesting, for any of your research career, if you're a PhD student, going into model selection, I think is a super difficult but very rewarding direction. So on the left-hand side, we have the 3D bulk flow, which is Navier-Stokes, and we have implicit collocation. On the right-hand side, we have shallow water type equations, 2D explicit collocation, and we need to make sure that we're not missing mass, that we are conserving things during the transfer. And today we won't have really the freedom to talk about all of these very important points, but this is the point. So we have models that are written here. We are using collocation methods. So this is called generalized finite difference methods. Essentially, this is a strong form approach. And you have coefficients that are written here. They are the matrix coefficients which allow you to discretize, let's say, the Laplacian. So if you have any partial differential equation, you have two approaches to discretize that. Either you discretize the space of solutions, that would be finite elements, or you discretize the operator, that would be finite difference. So in finite difference, you say the derivative is approximately f of x plus delta x minus f of x divided by delta x, or you take one on the right, one on the left. So f of x plus delta x minus f of x minus delta x divided by 2 delta x, that gives you the central difference. You can do that. That gives you that for a very standard structured grid. That's trivial because you look on the right, on the left, divide by the length. Now, if you have an unstructured cloud of points, that's more interesting. It's called generalized finite difference. It's called point collocation methods, all sorts of names. At the end of the day, it boils down to being able to capture these derivatives locally and compute them using the local neighbors that you have around the star point. And that can be done, and Pratik wrote a lot of papers that review this and also help you select the best stencil, which is the neighboring points, in order to maximize the accuracy of the method. So that's now well understood. We wrote quite a few papers on that. I can send them to you if you're interested. But what it boils down to is I give you a set of points randomly distributed, and I ask you to compute locally the gradient operator, the Laplacian operator, and because it's collocation methods, I didn't say that, but you do not have the niceties of finite element Galerkin methods or weighted, well, it is a weighted residual, but the weight is a Dirac delta function, so it's not very smooth. And so you don't have all the beauty of the finite element method where you integrate once, so you get rid of one order continuity in the trial and test functions. Now you need to have continuous functions. That's why people use things like, you know, B-splines or web splines or whatever, very smooth polynomials, so that they can have continuous derivatives. So that's why we end up with that stuff. Okay, obviously, why mesh-free? I think it's trivial. If you try to do that with any Lagrangian method, you're going to have problems very quickly because of mesh distortion, elements that disappear, that have negative areas and volumes and so on. So don't even try it. I think it's really not the proper discretization scheme for that. We want to do adaptivity in that way. So we have bulk and thin film. We have an interface here, which is some sort of overlapping domain decomposition. You can think of it that way. And we progressively transform that area volume into a thin film and then move on. So that's basically the idea. I cannot do justice to that theme in the time we have, but I just want you to know that we're working on this way. If you're interested, you can always come back to us. So the way it goes is like that: model transition, point cloud organization, 3D solver, 2D solver, post-processing. That's it. There is a lot of work trying to figure out what is the shape of that point cloud. So effectively, is it very thin or is it bulky? To do that, we use principal component analysis, so PCA, because it gives us an idea whether something has almost all eigenvalues of equal size and equal directions, eigenvectors of same direction. That means that you may have something spherical, or if you have a privileged direction, which means that the thing is very elongated. So this is a purely geometrical approach to finding out if something is elongated or not. And we could use probably a lot of very much better methods, but this is what was done in that case. Yeah, that's it. Then we have a criterion on how to change the models, and we have another problem, which is the projection, because of course you have different types of models, therefore you need to project from one model to the other. You have interface particles, you need also to handle that. So that is a difficulty that needed to be looked at. Yeah, and you see this is applied in areas like geosciences, which is interesting. Okay, ghost particles and so on. At the end of the day, I'm just going to show you the results. So if you look at that, you see the flux versus instantaneous flux versus time. So there is a lot of, let's say, oscillations. But, well, you see that the trend generally is correct. Okay? And here you see the cumulative flux where things go. Of course, there is some sort of slow divergence from the exact solution, which is purely 3D, to the coupled solution. But for now, it looks pretty good. And now, if you look, this is another example where you look at cleaning effect of a jet that's impinging upon a surface. And you compare adaptive to the standard one, and you see that the results are not that bad. And then you have very fancy simulations where a car is traversing a thin layer of water. And this is how it looks, because Volkswagen was interested in this in order to figure out what is going on in terms of things like aquaplaning and all sorts of different things. And I think that's the end. Unfortunately, I'm very slow and late, so my apologies for this. And thank you for your attention, and sorry if it was a bit all over the place, but I wanted to do justice to many people that did a lot of work, and also to give you something that you could sink your teeth into, because you're in that area of fluid, which again is not my field originally, so you have to excuse any inconsistencies or inaccuracies in what I said. Thank you very much.
It's more interesting looking different topic you've been talking about today. So any questions from the audience? Yes?
What information does transfer between the 3D model and 2D model, and is it going to be two-way, the information is going, because you are not solving at the same time these two models?
Yeah, so again, in terms of, to get a precise answer to that, we will need to talk to Pratik to be absolutely sure. But from my discussions with him, what I understand is that that the coupling is done using the primary variables. So you have, let's say that your unknown is velocity. If you have an Navier-Stokes equation, you're going to have a very rich amount of information along the plane, for instance. On the other side, you'll have the shallow water equations where you have effectively one variable which you need to couple. So on the interface, what is done is that we are writing conservation equations in order to make sure that there is no loss in the energy. But this is a typical problem we have also in solid mechanics, when we are coupling a thin shell to a 3D bulky volume, because the thin shell has rotations, but the 3D volume has only translations that lead to rotations by combination of translations. So we need to transfer one to the other, and usually it's done using constraint equations. And so this is the way that is done. And yes, there is bilateral transfer.
Other questions? Also, people online, any question online?
I guess you never know. Everything is working here.
Yeah, it's working. It's about 20 people online.
20 people online. All right. I don't know what we're seeing here. Yeah, so online, I guess it's not so easy to ask questions, unfortunately.
If you have a question, you may raise your hand or just use the microphone to speak, ask your question. No.
Don't worry, it's fine.
No, okay.